Nazreen, the floor is yours. She's going to talk about 2D TQFT and Frobenius algebras. Nazreen, you're most welcome.
Thank you, Sarah. Okay. I hope you can hear me. Right. So hello, everyone. Once again, my name is Nazreen Farha. As she has said, I recently graduated with my MSc from the University of Nairobi, and I'll be talking about two-dimensional TQFTs and Frobenius algebras. So what are TQFTs? In full, it stands for topological quantum field theory. And it stands for topological quantum field theory, and it is at the heart of the three disciplines: topology, quantum mechanics, and field theory. So when we study TQFTs, they are physical. TQFTs are a way of studying physical systems, as I said, in a purely topological manner, right? And they are at the heart of topology, quantum mechanics, and field theory. So it's fascinating to see that this physical object, has connection to something that is in algebra, the Frobenius algebra, right? So we'll explore this connection, and we'll build it through pictures, right? So for us to understand how a TQFT works, I'd like us to imagine that we have a set of lines, a set of circles arranged in a line. So these circles are free to move, and they can merge, right? And they can split apart in the process. So if we were to trace the surface that they form in time, we'll see that, and look at the initial and the final configurations of this circle, we will see that the surface they form is what we call a cobordism, right? So cobordisms form a category, that is the category of cobordisms, and they have dimension in it. And in our case, we'll be looking at two-dimensional cobordism category, because we want to establish a connection with the Frobenius algebra, and we'll see the connection lies with the two-dimensional TQFTs. So a TQFT basically transforms this cobordism category into a different category, in our case, that of vector spaces. And in the process, we gain some information that has been preserved, right? And TQFTs are of interest to mathematicians because they actually generate invariants. They generate invariants. For example, Edward Witten showed that the three-dimensional TQFT generates invariants that we call the Jones polynomial, and they are related to knots and links, the knot and link theory. So for the physicist, TQFTs are of importance to them because they act as toy models because they have some particular characteristics that are similar to those of the theory of quantum gravity. So it acts as a toy model to study, if you want to study the full-fledged theory. In that case, usually in the TQFT, we have the closed manifolds, which would correspond to the space. Then the cobordisms would correspond to space-time. And then the vector spaces would correspond to the state spaces. And the operators in these vector spaces are the time evolution operators, right? So as I said earlier, this theory is topological. That means it does not depend on any metric structures, right? Or any additional structures. So it is enough to just draw them using, and you can squish them and all the fun stuff we do with topology. So these are some of the motivations. I've already mentioned two of them. But another beautiful thing about TQFTs is that as I say, it's an interdisciplinary kind of thing, right? And it shows us how applicable mathematics is, and not only just the applicability, also it's the beauty of mathematics. And this is something we all aspire to. This is, I hope, why we all do mathematics, not only for the applicability, but because it's something beautiful to study on its own, right? So here, a brief literature review on Frobenius algebras and TQFT. So Lowell Abraham, he gave a representation of monoidal categories in 2 dimensions in terms of generators and relations, and we'll see that this is useful for us. And later on, Lovaux, he characterized Frobenius algebras using comultiplication, right? And this had been revisited by others like Frank Quinn in his lectures on axiomatic topological quantum field theory. So since we plan to highlight the result that there is a connection between 2-dimensional TQFTs and Frobenius algebras, it's nice to mention that Robert de Graaf was the one who first documented it, as far as I know, yeah, in his thesis. And then an advancement on this was by Joachim Koch, right, who was able to show us that we can actually view that the free symmetric monoidal category, the cobordism category, in terms of a commutative Frobenius object. So it's a generalization of the theory that we had already. Okay, so we'll now go on to build the theoretical framework that we need to actually study this relationship between these seemingly different things. So we know a C algebra we will work on you can work with any field, but in our case, we'll be looking at the complex field. So a C algebra is a C vector space that is equipped with a bilinear product of vectors. And a Frobenius algebra, as we know, is actually a C algebra that is finite dimensional, associative, and unital, and it becomes Frobenius if there is a non-degenerate bilinear form on it, right? And we will call it the trace. And the Frobenius algebras are symmetric if the trace is symmetric, and it can be commutative. Okay, so a good example of the Frobenius algebra that is a bit more common knowledge, I hope, is the matrix ring. Yeah, so the matrix ring is a Frobenius algebra with the usual trace map on matrices being the Frobenius form. Another one would be the field, the algebraic field extension ring, right, over C. And then because we know fields have no non-trivial ideals, any non-zero C linear map from the extension to the complex field will do as a Frobenius form, right? So we also need the notion of cobordisms, right? As we said earlier, TQFT transforms the cobordism category into the category of vector spaces. So a cobordism is an n+1 dimensional manifold that is between 2 n-dimensional closed manifolds, all right? So here we have an example of a cobordism W, right? That is between the 1 dimension, it's a 2-dimensional cobordism because it's built from circles, and circles are 1-dimensional. So we have M here as the input boundary, and n prime as the output boundary. So one thing to note, I'll be reading my cobordisms from top to bottom. That is important because some people read it from bottom to top, but I want to read it from top to bottom. Okay. So because we'll be working with categories, I feel it's important for us to revisit some notions from category theory. So a category C is basically a collection of objects with a set of composable morphisms between each pair of objects, and every object has an identity morphism. And the identity morphism, and there's the element of composition. As you can see here, we have the objects X, Y, and Z being composed. Okay, so, and the identity morphism sends an identity element for the acts as the identity element for composition. Okay. So an example, we have 2 examples that we will encounter from categories would be the category of vector spaces, in this case of a C, right? The objects would be n-dimensional C vector spaces morphisms would be linear mapped, and then the composition of linear maps would be described by the matrix multiplication. And the identity for any vector space would be the map that takes the vector space to itself. Now, the category of cobordism is also another category that we will also see. So its objects would be the n-1 dimensional oriented compact manifolds. And then the morphisms in this category are the n-dimensional cobordisms. The identity morphism is the cylinder, is actually not the cylinder is the identity morphism for the 2-dimensional category of cobordisms, but in general, the identity morphism for the n-dimensional cobordism category is given by the object times some interval, and then the resulting cobordism would be the identity cobordism, right? And then the composition operation is given by gluing. So one thing about cobordisms is that they can be glued together as long as they have the sufficient number of similar incoming, let's say we have, similar incoming and outgoing boundaries where we are supposed to glue them, the number, So, and that gluing is what gives us the composition operation in this case. And then because a TQFT we said takes the cobordism category and maps it to the category of vector spaces, it is a functor, So what is a functor? A functor between any two is a map of sorts between categories, right? So it assigns to each object in one category another object in the corresponding category, and the same to morphisms, right? So the 2-dimensional cobordisms, the 2-dimensional category of cobordisms is built from circles, which are the 1-dimensional manifolds we'll be working with, right? And then the morphisms are built from 4 building blocks, which we have here. This is the cap, the pants, and the copants, right? So the cap, as you can see, it represents the depth of a circle because we have the circle, and then the circle is mapped to nothing on this side. And then the cap with an A represents the birth of a circle because it comes from an empty manifold, right, to the circle. So it's like basically the birth of a circle. Okay, so the pants and the copants, the pants, obviously the name, as you can see, comes from the fact that we have, they look, if we were to squish it or stretch it in a way, we'd have the pants, right? And then when we flip the pants, we get the copants. Okay, so the identity morphism in this case, as I said, is given by the cylinder because it takes the circle from and maps it to itself and takes it to itself. And here you have an example of the cylinder being composed with the cap, and then we actually get the cap back. So as I said earlier, composition for the cobordism category is done when we have the same number of outgoing boundaries on one of the cobordisms and the same incoming boundaries on the other cobordism, right? So here we have A and B and A and B, and we can glue them in this manner. Then this would be the composition of cobordism. Okay. All right. So the category of cobordism is actually not only has extra structure on it, and that structure makes it a monoidal category. We'll see what it means to be a monoidal category. So a category is said to be monoidal if it has a functor on it that is called the monoidal product, and if it has an object that we call the unit object, and a family of isomorphisms that are associative, and that can be left multiplied with the unit and right multiplied by the unit as well. So for the category of cobordisms, the tensor would be disjoint union of objects, and then the unit would be the empty manifold, right? And then it is also symmetric because the disjoint union of manifolds is actually symmetric. Okay, and then because the TQFTs are functors between between symmetric monoidal categories, that is the category of cobordisms and the category of vector spaces, then it makes sense for us to say what a symmetric monoidal functor is. It's just a functor that preserves both the monoidal structure and the symmetric structure of its category. Okay. So now we formally state the definition of a topological quantum field theory, an n-dimensional one. So an n-dimensional TQFT is a symmetric monoidal functor from the n-dimensional category of cobordisms to usually some additive symmetric monoidal category. In this case, so as I said earlier, the category of vector spaces, okay, over the complex field. So this joint union would correspond to the tensor product of tensoring of vectors, and then the empty manifold would correspond to the ground field, C in our case, the complex field. Yeah, and then cobordisms will be mapped to linear transformation. So one thing to note about the TQFT is that the image of the TQFT inputs is actually finite dimensional, right? So because, yeah, it's finite dimensional. So now for the two-dimensional TQFT, it consists of a C vector space. We will call it A, right? And then A is the image of the circle under Z, right? And Z is an example of a two-dimensional TQFT. That is the notation we use. So, and then we have 4 operations on the two-dimensional TQFT. We have multiplication, we have co-multiplication, which is given by mu, and then we have the co-unit, which is given by epsilon, and the unit, which is given by I. Okay, these are the notations we're using. So the multiplication of the in 2D TQFT corresponds to the copants, and then the co-multiplication corresponds to the pants, and then the co-unit corresponds to the cap, that is the cap with an A, and then the unit corresponds to the cap with a U again. So we will see how these two-dimensional TQFT acts on the manifold, and then the resulting, and how the resulting vector spaces behave. Okay. So because we know that the two-dimensional TQFT is a functor from the two-dimensional cobordism category, the category of vector spaces, then the n-1 dimensional manifold in this case would be the circle, right? Okay, because it's topological, we can squish it, and it is still the circle, right? So when the TQFT acts on the circle, we get the vector space A, and then for any cobordism, n-dimensional cobordism, normally the corresponding boundaries are mapped to vector spaces, right? So here we have the multiplication. So when the TQFT acts on the co-multiplication, so when the TQFT acts on the pair of pants, we get this multiplication operator, and it's called multiplication because in the normal sense, how do we multiply? We take the reverse of multiplication. The reverse of multiplication, so I think it's better, let's start with multiplication. Sorry about that. So yeah, so when we have the functor, the TQFT acting on this particular cobordism, right, which is the copants. So we have 2 inputs, and then we get 1 output, and we call this particular resulting map the multiplication. And why multiplication? Because in the normal sense, when you have multiplication, you have 2 inputs giving us 1 output. And in the same case here, we have 2 inputs giving us 1 output. So intuitively, that is why multiplication. And then now co-multiplication, as I said, is the reverse of multiplication. So we flipped the cobordism up, and then now we have 1 input and 2 outputs, right? two outgoing boundaries. So again, this is the co-multiplication. So this actually alludes to the notion of duality, and we'll see that it actually is there. Okay, so the identity on the TQFT is the cylinder, and so the TQFT would assign it to the identity map, right? So it will be the map that maps the vector space A to itself. And as we say, the empty manifold is usually mapped to the ground field C. And here we have, since the depth of a circle is a cobordism from the empty manifold to the circle, then the resulting map under the TQFT would be from the ground field C to A, and that is the unit, as I said earlier. And the core unit is the depth of a circle. Okay, and then this is its map. Okay, so composition of cobordisms, we have to, as I said, we usually glue corresponding outgoing and incoming boundaries, and then there is they correspond to the tensoring, right, of the corresponding vector spaces for each of the boundary. So here we have an illustration of the composition of cobordisms, and after the TQFT acts on the cobordism that is formed, the resulting map is of this. So we can entirely just say it's from V cross V to V cross V, where V is the vector space. Okay. So why the interest in TQFTs? As I said earlier, TQFTs are of interest to mathematicians because of the fact that they generate invariants, right, of closed manifolds. So here we have a closed manifold from the empty circle. So from the empty circle to the empty circle. And if we apply a TQFT onto it, we will see that it actually corresponds to the linear map from C to C, which is scalar. Yeah. And then the torus is also an example of a closed manifold. So if we split it into two, it becomes two U-turns. So it's from the empty manifold to the disjoint union of two circles, to the disjoint union of two circles, and these two circles, and again the union of these two circles to the disjoint, to the empty manifold. Okay, so once we apply the TQFT onto this structure, we see that the resulting map is also a scalar map, right? So these scalar maps are what we call the invariants. Yeah, and there's a popular example, I had briefly mentioned it earlier, of a two-dimensional TQFT is the Chern-Simons theory, right? And this Chern-Simons theory gives us the Chern-Simons theory, right? So now we are taking a look at the relations on TQFT that are built from the cobordisms. Okay. So first of all, we have that I, which is the unit, is actually the unit of multiplication, and epsilon, which was the co-unit, is the co-unit of co-multiplication. And how does this happen? So when we glue the cap onto the copants, we actually get a cylinder, which is the identity, right? And then when we look at the corresponding maps under the functor, we see the result is also it's the identity map. Yeah, and where A again is our vector space. But then and then for the pants, for the pair of pants, when you glue the cap, we again still get the cylinder. Again, therefore, we have seen I is the unit of M, and epsilon, the map, is actually the co-unit of co-multiplication. So this TQFT is actually associative, right? And it's associative because when you look at this composition, they're the same. Whether we glue the copants onto the copants first and then followed by the cylinder onto this pair of copants, or we do it the other way around, the result is the same. This is because if you look at the input boundaries, we have 3 at the top and 1 at the bottom, and 3 at the top and 1 at the bottom. So if you apply the functor on it, we get that we still have the tensoring of three tensorings of A, that is A cross A cross A, and A, all right? And then for this one, again, for the co-multiplication and the identity, whether we glue first the copants followed by the cylinder, or the cylinder followed by the copants, is basically the same. So this implies that multiplication and co-multiplication are both associative, and thus A is actually an associative algebra. Okay, so it is not only associative, it is also commutative, and this is given because this is due to this braiding structure that we have here, and the fact that these 3 cobordisms are actually equal. And the same goes for the co-multiplication. Due to this braiding over here, and the equivalence of these 3 cobordisms, then its co-multiplication is also commutative. Right? So A is both a commutative algebra and a co-commutative algebra. All right. So when we glue the copant to the cap, we get a U-turn, and when we glue the cap to the copant, we also get a U-turn. So these U-turns actually are the bilinear pairing that we know from Frobenius algebra, where the first one is the bilinear pairing, and its co-pairing is given by the second U-turn. So this bilinear pairing is actually symmetric, and it is non-degenerate. It's non-degenerate because if we compose these 2, or if we glue these 2 resulting U-turns, we get the cylinder, right? And then this implies that the composition of the co-unit and the multiplication and the composition of the unit and the multiplication is actually a symmetric bilinear form on A, right? And it is non-degenerate. So we have seen that A is an associative commutative algebra with a bilinear form. And it is also, A is dual to A prime with respect to the non-degenerate bilinear form we have defined. Okay. So now when we take a look at, when we combine co-multiplication and multiplication, we see that they are dual to each other, right? They're dual to each other. And this is, when you follow this diagram closely, it follows from it. And also from this picture, which is actually the Frobenius relationship on A, right? It shows that the co-multiplication is a map of bimodules because M is, right? And this is actually the Frobenius, as I said, the Frobenius relationship. So far we have defined an algebra that is associative, that is commutative, and it has a symmetric bilinear form that is non-degenerate, right? And it also has the Frobenius relationship on it. So basically we have defined a Frobenius algebra, right? So we have thus established a connection between the 2-dimensional TQFT and the Frobenius algebra. So this leads us to my conclusion, right? That is, we have a bijection of sets between the set of 2-dimensional TQFTs over the field C and the set of commutative Frobenius algebras. Okay, so yeah, that's the end of my talk. And these are some of the references I used. If you have any questions, please do ask. Thank you.